compactness first, and completeness, right? Because okay, actually, let's just do what we, yeah. I can talk about compactness because the way we defined compactness was using sequences, right? And so I think Aryan knows the sequences, and so obviously he knows also. I think that's fine. We'll do, and then gradually we'll push in the extra stuff. So what do we want to prove, right? So I think we wanted to understand the relation between, relation. So we'll define these things between locally compact. So this will be described, right? Between locally compact normed linear spaces. Yeah. And of course, I suppose for even if you have seen the definition, it may be new to you. So you have to extrapolate and, just take the closest approximation that makes sense to it. So we had locally compact norm linear spaces, right? And we want to see the relation between this and maybe characterization and, yeah, characterization of compact sets in such spaces, right? Okay. So first of all, you should look at the, first of all, you can look at the basic example, right? So what's the basic example of a non-linear space? Okay. So when I say a non-linear space, yeah, I mean it's a linear space with a norm, right? So what will be an example of a non-linear space? By linear space, I mean a vector space, right? So that's the first thing. We should be able to give an example.
Sir, I just R with Euclidean.
Right. Okay. So already, yeah. As that's a good example. Some other more interesting example. I mean, that's interesting, but we just want to take higher dimensions, though it doesn't not. So let's take Rn. Okay. Rn.
Then we can take the max. I forgotten the name, but we discussed that norm like a few months ago.
Right. You can take that norm and it will give us the same thing. But I will take the usual. I will take the Euclidean norm. Okay. Yeah. I understand. So that's the max norm, and maybe I'll discuss all those norms give you equivalent metric spaces, which is another interesting, which is another aspect of equivalence of spaces, but which also is a notion we have touched upon in the past. But then there is this. Okay, this is fine. Is it okay for everyone?
Yes.
Right? Yeah.
Yes.
Okay. Good. Okay. So now the statement is that Rn, just like any norm linear space, this is a metric space. Okay. And what is the metric D? I don't think I need to say, but okay. So this is an example of a non-linear space. So that concept is okay. Now, locally compact. Locally compact. So, well, the definition of locally compact was that there is a basis of compact around any point. There is a basis of compact, or rather, there is a basis, right, whose closures are compact sets. What does that mean? So, or maybe I will, okay, let's keep everything. So locally compact. So uh, I should just ask, let's look at, yeah, let me not define locally compactness. Let me give an example why this Rn with this norm is locally compact. Okay, then you can understand. So look at this. Look at a ball of radius r, any r, okay, around the origin. So maybe I will just use this notation, or no, that notation can be a little confusing. So let me use this notation. Yeah. So this is okay, right? Ball of radius r around the origin. And obviously, I mean, if you would want to, if you have done the homework to check that that the norm linear space is a metric space, that's a good exercise to get, yeah, do that. I suppose you have done. So, but look at this set BR0. Okay. So what is this? This is just means I'm just finding it. Yeah, I'm writing 2 here. We will understand why. R. So I'm putting strictly less than. Okay. I'm putting strictly less than. Okay. So you look at this set. And now you look at the closure of this set. Okay. So closure is just, if you know the definition, and if you don't know the definition, I'm not defining it right now, but it is just, in this case, it turns out to be just, we just add all the limit points, right? So we just take the boundary as well. So you get this set. So now you have these two sets. Okay. Now this open sets, right? These are open sets, right? Basic sets. And if you take them, if you take this collection of open sets, right? Yeah. Let me not just say more, but I'll just say take this collection of open sets. Otherwise, I'll end up trying to define what is a basis and so on. But that's not important to this discussion. So yeah. You take this collection of open sets, okay, and then you look at this collection. All right. Look at yeah, you will look at this collection. So this is all getting very repetitive. Okay. Yeah. So what I want you to show, or maybe I'll just say roughly. So for those of you who know what is locally compact, if you know the definition, then you can see where I'm going. And if you don't know, it's not a problem. You just try to prove what I'm asking. Just try to see this, why this is true. Yeah. Because I'm stating it without locally compact, without the language. And most often it will be stated without that language at this stage. I mean, at this stage, meaning that if college, if yeah. But soon enough, this definition itself is needed. Using this word itself starts to become important. But claim is that given any sequence, okay, given any or maybe uh, given this thing, right, inside this R, okay, So now you have taken a sequence inside this. I mean, you can just imagine V2 and R2, right? And you can just do, right? Right? Show, I mean, there exists subsequence. Yeah, so this notation itself implies that it's a subsequence because I'm taking I. No, if I use this notation ij, it does not imply. There exists this, a subsequence.
So shouldn't it be J 1 to infinity?
Right, yeah, should be J. Correct. Yes, yeah, but yeah, and I'm still writing that this is a subsequence, because otherwise it's not, doesn't follow logically, though obviously you still understood, but I should be logically precise as much as possible. So if I look at this so I'm saying that there exists a subsequence which converges to a point in BR, right? And this is really nothing. This is just kind of buying some time. Kind. It is nothing, right? Because you can just prove it. Yeah. So if I have to just give you some sort of thing, then how do you say? How do you say? How do you say? How do you say? Right? How do you say? Well, you can just quote the Heine Borel theorem, if you know, right? That closed and bounded means compact, and then you can say. And if but obviously, if you don't want to use that language, that language provides the answer directly. But otherwise, it's very simple. Otherwise, also is very simple. You just consider this xi, and if you think about it, then what is this? This is just kind of, I'm just writing the coordinates xi2, right, till xin, right? And now you look at the first coordinates. So you look at this this sequence, right? Correct. You can, if you want, you can write it like this. No, this is not what I want to write. So that's not squares and cubes. Okay, that's not squares and cubes. This is just the first. This is just the first thing, x1, right? So you see what I'm doing, right? It's a sequence of sequences, right? So this is a sequence. I mean, this sequence itself, this term itself is a sequence, right? Maybe putting a comma is not bad. And then you look at again. So again, it, yeah. So suppose, no. So see, I'm confusing myself. Yeah. So this is just a second term, and so on, right? But then, okay, so that's why, right? So, of course, this thing will end, right? This is not infinite. I have not taken R infinity, though you can take that and you can ask the question. And there I yeah. So what happens there? Yeah, I mean, it will start to depend on a lot of things, right? So let's not talk about it right now. You can think about that. this. And now basically, but what's the main matter here? The main thing is that this is a sequence in R, right? And you know that this has a convergent subsequence, right? So this is I'm giving the idea, I'm not providing a proof. The first coordinate has a convergent subsequence, correct? So you take that convergent subsequence, right? And then you look at the second things, right? You look at the second column, correct? And you consider, you take only that subsequence now, right? You consider only those rows for the second column and take a subsequence of that subsequence which converges. And you go on and on and on. And you stop in finite time. And that way you will get a convergence subsequence. So I'm just using Bolzano-Weierstrass for R, that every sequence has a convergence subsequence. Every bounded sequence, obviously everything here is bounded, you are inside. Okay. So that way you will get a convergence subsequence finally. And that convergence subsequence will of course lie in this. I mean, the limit will lie in this because this is a closed set. You can prove it by hand also directly. So this is the idea. Okay, I mean, this is the idea. You can just go back and prove. Okay, so this is basically, if you prove this, then you have basically proved the Heine Borel theorem. So, so it cannot be so easy. It cannot be one liner, I suppose, right? Heine Borel theorem, yeah. So you see what we have proved for the language, then you see that it's locally compact, because all these local objects, all these small objects, I mean, all these local objects, they are all compact, and they are, yeah, and these objects can, kind of approximate towards zero, and they are all compact. So that is, yeah, and there are easier definitions of locally compact, but then it's harder to see why they are. Anyways, okay. But this is not like, this is just something. This is Heine Borel theorem. So now let us get to the actual question. Okay. And now I will say the actual question without the language of locally compact. Okay. But relate. Now imagine you have a norm-linear space. So now this Rn will get replaced by any vector space, but the field should be real or complex. Otherwise, you see, you cannot really do metric, and you cannot apply norm and so on, right? So for that reason, so let's forget C, just focus on R. But the dimension we don't know, so that's one of the problems. Okay. So I will not talk about the infinite case today, but in this case, we are not assuming anything about the dimension. We are just saying that it's a vector space. So now you see, I'm gradually going towards the generalization, but this is not how I will usually do. My approach here is to go do the general case, and then you see the special case by specializing and putting the effort. Okay, so that I mean, you may not like that approach, but I mean, yeah, you can tell me when it's, yeah. But this is, let's continue. Yeah. So now you see, I've replaced this 2 norm by a just arbitrary norm. You don't know what that norm is at all, but it has the properties of norm. You understand, right? Properties, triangle inequality, blah blah blah. All those things. Yeah. And you can prove, because I introduced this last time, for those of you who were there, you should prove that this is also a topological group. Okay. Any normed linear space is a topological group. You should prove that. Okay. But it's not, it is important. I mean, it helps you in some way, but we will not go there right now. Yeah. But coming to the matter, the question now is that given a norm linear space, yeah, this is the norm linear space. Now suppose you are given and this is basically this is equivalent to local compactness, but just think of it like this concretely. Suppose you are given that these sets right, which is, I'll just once again write it, are compact. Okay. Suppose you are given that these sets are compact. Okay. And for all n. All right. I mean, so compact here, I just mean that every sequence has a convergent subsequence. Okay. And it's a metric space, so you can define convergence, just obvious things. So compact, you can take that definition, and that's a definition which we are going to use. I mean, suppose that's a definition that's you can take. There is an open cover definition, but that's not actually used much in this side. So okay. Then claim is, this is what I asked last time. If claim is y in x is closed, which you understand, it just has all its limit points, and bounded, which also is understood, implies y is compact. And this is the claim. So you see, this is very similar to the Heine Borel theorem, right? So this is what I had asked to prove last time. Let us just see it. Again, I will not give the complete proof that you should check out. I mean, so as I had given a reference, this is a book, Shirali, Satish Shirali or Shailesh Shirali. So I'm just writing Shirali because I don't remember the exact Shirali. And I think Hari Vasudevan or something like that. I mean, yeah, I think this was the name. And metric spaces. So they have a section on non-linear spaces. They will have these results. I'm sure they also have locally compact space sections, so they will have all it separately. So you can look at those two sections for the proper proofs. But I want to give the ideas, and because there is a lot more interesting things to do in this topic than checking details. Yeah. So how do you prove this? Let's draw some pictures. This maybe we can do with pictures. So, right? So you have a closed and bounded set. So let's say that it is like this. It's closed and bounded, right? Now you know that it is contained in a ball, right? It's closed and bounded, so it will be contained in some ball, right? Obviously, that radius might be very big, but it will be contained in one closed ball. Means just take the ball and take its closure. So it will be contained in some closed ball. Okay. These are basically ideas of Heine Borel theorem proof and so on. I mean, I'm not doing anything actually. Okay. These are the things that I used in Heine Borel also. Or, yeah. So y is contained in a closed ball, right? Closed ball. Now, if b of 1 by n 0, if this is compact, right, this implies that b of anything, right, b of k is compact. This you should prove. That it doesn't really matter. If I know one ball is compact of any radius, then if I stretch it or stretch it, dilate it, if I change the radius, all those balls will be compact. I mean, the closed balls, open balls obviously cannot be compact. All those closed balls will be compact. Fine. That you can prove. Hello, am I audible?
Yes, sir.
Yeah,
Oh, okay.
Yes, sir.
Because there was some, yeah, okay. If I'm not audible, then you can just send me a message in the chat also. Somehow this, okay. This you should prove. This also follows from the fact that it's a topological group. We said last time, right? That those operations are okay. No, it actually doesn't follow from topological group, maybe, but this you can prove easily. Okay, so you have to prove that in this kind of space. I mean, that's what you use in R also, right? That multiplication by a constant. If you take a function from R to R, which is multiplication by 2, that's a homeomorphism. Means that's a, you know, that preserves everything. And then, yeah, sequence converges here, then 2 times all the terms of the sequence will also converge, and so on and so on. So this is a rather trivial business, right? Yeah, any sequence is take, then you shrink that sequence inside one of the balls, that has a conversion, then expand that sequence, and that this will converge to that one, and you can prove all that, right? So that's it. I mean, that's the mostly the end of the proof, right? Why is it the end of the proof? Because of this ingredient. So you know that this ball is compact, and this is a closed subset. So another fact is closed subset of a compact space is closed. And you can take the sequence definition and you can also prove it's not hard. Closed subset of compact is closed. Okay. So sorry, is compact. It's compact. So it means that Y is compact. That's the end of the proof. Just see if you have any problems. We'll meet after 10 minutes. I mean, because it's going to end, so that's why. But yeah, this is the very simple thing. Yeah. Basically, you can dilate the topology. That's why a local phenomena has an effect. I suppose that's the only thing. Yeah.